So hello everyone, welcome to the week 10 of Coherence and Quantum Entanglement course by NPTEL. As you all are aware about that I am your TN Nilakshi Shanapati, and this is the course which is instructed by Professor Anand Kumar Jha. And we have already reached to week 10 at almost at the end of the course. There are only 3 weeks left. Today is the week 10, and if after completing this day we'll have just only 2 weeks. And as I told you from the beginning that as the days will pass, and we will have much more in new and very interesting topic in this course which we are covering at this moment. Today already we are going to, you have already learned about the Bell's inequality and EPR's Einstein-Podolsky-Rosen paradox, and how what is EPR measurement, what is Bell measurement, what is the entanglement, what is quantum entanglement, how do we generate entanglement of photon, and each and every things which you are waiting for to learn, those are actually running at this moment, which is very interesting for you as well as we obviously enjoy these things. So today our plan is to again to first I will start with the previous day's problem, which we started but did not complete it. Rather, I have just given you the hints and just discussed. Today we will start from that, and we will cover the whole question, and then of course we will discuss about the Bell inequality, the hidden variable theory, and what are the EPR measurement. Although those things are covered very well and elaborative manner in your lectures, but as I usually try to give you the recapitulation or recap or the short summary of the lectures, so that's what we will discuss today. And of course these topics are very important and interesting, so it will be very helpful and enjoyable to discuss also. So that is there, and apart from that we will solve more new questions, 2 or 3, and end up today's discussion session. So this is the plan is like similar like other days, but some more enjoyable topics for you we are waiting for today's class. So as before, this was the synopsis of the whole thing that is going to happen today. But before that, as I always mention all the details, so I will again mention all the details, because although this is at week 10 and you guys are well aware about all of the things like in very good manner, but still let me formally introduce all those things, because maybe somebody has skipped somewhere or forgot that those things. So this is a Coherence and Quantum Entanglement course by NPTEL, where whatever the materials I am using, all of the slides, all of the class notes, and sometimes some extra materials, everything are present in the Google Drive folder. I will share the Google Drive folder link once with you through the chat box of this course, of this Google Meet link. So this is the Drive folder link, and this is the where you will get all of the materials. And if you somehow miss any of the classes and any of the discussions, and then of course you can see it on your like whenever you want to see it at your convenience. That for that reason these videos are actually recorded, and these videos are uploaded in the YouTube channel. This is the YouTube channel where you will get all of the videos. You can see all of the other classes videos are already uploaded, and this is the channel link I am sharing with you in the chat box. So if you, and most importantly, if you have any questions regarding the, let me show you. I have shown you on the in previous class also, but again I am showing you that if you have any queries, please ask and discuss those questions or queries in this chat section of the chat, I mean in the chat section or the message section of this Google Meet, where we meet every time, and this is the platform where you can ask the question. I'll be very happy to discuss them lively with you. I mean, in the live manner, like now we can discuss and talk among ourselves, so we can do that here. And if you see these videos later on and want to ask some question, then of course you can write into the chat box of this YouTube channel of the respective video, corresponding to the respective video. And I also always share my email ID with you. You can write or drop me a mail anytime. I will be very happy to answer. Many people actually mail me, and I used to reply them. Mostly they ask for the soft copy of the books and so on, so I try to help them in in every manner. Sometimes people also connect with the LinkedIn, so that's also okay. Although that's not a recommended media, but it's okay if you want to ask something there, because I found some people there who also asked me in the LinkedIn. And of course you can you can see that there is this Q&A option, that is ask a question portal of this NPTEL. You will be able to see this is like this. So okay, there the questions are actually posted, and we used to answer them on a regular basis. You can see every questions are answered. These are some new questions which I will try to answer, which I of course I have not seen and I need to answer. So there are many questions, many people ask questions, and we used to answer them in that ask a question portal also. So these are the media through which you can contact with us regarding this regarding the discussion of this of any material of this course. Okay, so let us after going through all of this discussion, let us first start, or I will start the discussion now with the previous day's homework problem, which I have discussed extensively in the previous day, but I told you that I will show the schematic diagrams of the two-photon path diagrams of these questions, which are there in the question. And then it will be very easy for you to grasp or to understand that what is actually happening. This is nothing but the standard procedure whatever you have followed for the Hongo-Mandel or the two-photon interference. Here also we are founding the coincidence count, and just by using the two-photon interference. So you just need to you just need to draw the schematic diagram of the two-photon path diagram, where you will be able to connect the RSI, that is the coincidence count rate, with the two-photon path length difference and with the path length difference and the path asymmetry. So our motive is always that whenever we get any complicated situation or setup for doing the for calculating the RSI, that is the coincidence count rate of the interference, then always for the two-photon case, then always we need to draw the path diagram, and we need to find out the path length asymmetry and path length difference. That means path length difference, that is delta L, and path length asymmetry, that is delta L dash. Once we know those things, then we can find out the coincidence count rate very easily. So here also in the first question it is telling that assuming theta nearly equal to 0 and theta is shown over here and kd equal to 0, find the coincidence count rate of the two detectors. Then second question is find the one photon count rate at detected ds and di from the same setup, and now it is referring to C, that is referred to the figure below. Assuming x equal to 0, calculate the coincidence count rate RSI as a function of the displacement y if the central wavelength of each of the signal and idler. Okay, we will come back to this question C whenever we will solve this. First let us solve this A and B part of this question. For that, this is the schematic diagram that I wanted to show you, and I mentioned in the previous class. This is the pump photon coming PTC through the PTC. Two photon is generating and it is moving through these two directions. It is passing through these two, it is reflecting through these two mirrors, and it is passing through this beam splitter. So what can happen? Either two photons can transmit, either two photon can reflect, either one photon can transmit while the other photon is reflecting, and vice versa. When the one photon is reflecting, other photon is transmitting. Okay, so based on these, let us consider first one, this case that two photons are transmitting or reflecting. For that we can calculate that for the coincidence count rate of the two detectors. Of course, when we will get the coincidence count at ds and di simultaneously within a time difference tau, which is very small, that will be only if both the both the things are transmitted and both the things are reflected, then only we will get the coincidence count. For that, the two photon path diagram is shown over here, which is and for that we need to calculate the phi s1, phi i1, phi s2, phi i2. This standard procedure is shown to you that how to find out that using the Hanger-Mandel in the lectures. It is very it is elaborated in very it is like stated in a very elaborative manner. So I hope you can understand why it is phi s1 equal to pi, because of this reflection at pi phase, that is a mirror, and then and that is why phi, and then it is again reflecting through it, which adds pi by 2, reflecting through the beam splitter, which adds pi by 2 phase. That's why the total phase is pi plus pi by 2. For the pi i1 also there is pi plus pi by 2, but there is some difference because of the beam splitter movement. Beam splitter can move of x in this direction, this up and down, and the angle is theta, so it will be 4x. How it is 4x, that is also discussed in your lectures. And now the second viable option is that both are transmitting, and for that there will be only one phase adding over there, which is the reflection due to the mirror, and this reflection due to the mirror, which are phi s2 equal to pi and phi i2 equal to pi. So now you can find out the path length difference is del L equal to 0. You can see, you can calculate, you know how to do that. You have the basic idea of calculating the path length difference and path length asymmetry from your two photon interference setup. This is just the two photon interference setup with some twisting, and you can once you have all the idea of path diagram, two photon path diagram, so you can find out delta L and delta L dash, and delta L dash is this difference, which is 4x, and delta phi is equal to 3 pi by 2, 3 pi plus 3 pi by 2 minus pi. So if you calculate, then what it will come is pi. So now you know what is delta L, what is delta L dash, what is delta phi. So the expression for coincidence count rate RSI of two detectors RS and RI is given by RSI, that is the coincidence count rate, equal to R1 plus R2 plus 2 root over of R1 R2 gamma delta L gamma dash delta L dash cos K0 delta L plus KD delta L dash plus delta phi. The expression for the one photon detection probability Rx at the dx in Rx at detected dx for any one of them in a two photon interference experiment is nothing but the summation of Rx yi, that I have already mentioned to you. That means if and it will be used in the next part of the question, but what we need to find out at this moment is just the coincidence count rate for the first question, which is telling that find the coincidence count rates at the two detector, which will be nothing but this RSI equal to 2R1 minus gamma dash 4x. Why? Because we are considering R1 equal to R2, that means 2R, and as R1 equal to R2, so it is RR. R will be coming out from the root square root, so it is R plus 2R gamma delta L equal to 0, means this term will become 1, and gamma delta L dash is 4x, so it is gamma dash 4x, and cos K0 delta L equal to 0, so that there will be no term for this. KD delta L dash, which will be 4x, which for KD will be it will also be, as KD will become 0, so it will also become 0, and delta phi equal to pi, so cos pi is equal to minus 1, so 2R minus 2R gamma dash 4x. So what we will get, 2 are common and 1 minus gamma dash 4x. So this is the two photon coincidence count rate for the first question. And the second question, it is telling, let us see the question again. It is telling, find the one photon count rate at detectors ds and di. So for the one photon count rate, what we need to do, that RSI, that means whatever we have got, and that with that we need to calculate the RSI as well as the RSS dash. Okay, suppose if both the things are there, then what will happen, because these are the two cases where either two of them are transmitting or reflecting. Now it is the case where where either of them, one of them is transmitting and another is reflecting, like this is transmitting, this is reflecting, and for the vice versa case also, transmitting and reflecting. It should be shown with this direction actually, but it's fine, you can understand that there will be two possible cases which are same. Now for these cases we are plotting the path diagram, two photon path diagram again, and phi s1, phi i1 we are finding, which are these. I will not state again that what amount of phase is adding for what. I hope now by now you can understand that mirror adds pi phase, pi by 2 phase is added by the beam splitter. So pi plus pi by 2 for whenever it is reflecting, and whenever it is transmitting it is just pi due to the mirror. So this is the total phases that is written over here. Now delta L equal to 0 for these cases, and delta L dash equal to 4x again, and delta phi becomes 0 for this case. So in order to calculate the count rate at individual detectors, we need to use the formula for one photon detection probability, which is this Rx equal to I equal to 1 to n Rx yi. So now for a photon arriving at detector ds, the entangled pair can either go to detector di or to the detector ds dash. Please note that to calculate the one photon count rate, we will have to consider detector ds dash, because in principle the entangled pair can go there. Therefore, the one photon count rate at detector ds will given by Rs equal to Rsi plus Rss dash. And figure 1c, that means these two has two alternatives that will lead to a coincidence of detectors ds and ds dash. From the two photon path diagram, we get delta L equal to 0 calculating from here, and delta L dash equal to 4x, and delta phi equal to 0. Again using R1 equal to R2 equal to R, whatever we have used for the previous case also, then substituting it in the equation 5, that is RSI equal to R1 plus R2 plus this is whatever is there. So if you substitute, then what you will get is RSI equal to 2R into 1 plus gamma dash 4x. Therefore RS equal to RSI plus RSS dash, which is RSI is 2R 1 plus gamma dash 4x, sorry, my mistake, this will be SS dash, and this is the RSI. Okay, so sorry, just be focused and be like, this is just a printing mistake, I hope you can understand. So one is 2R 1 minus gamma dash 4x, one is 2R 1 plus gamma dash 4x. If you substitute and add them up, then what you will get is nothing but 4R. So that is the one photon detection probability, shows no interference at di. We get the same result for one photon detection at ds, again some printing mistake, and we get the same result for the one photon detection probability at di, that is Ri equal to 4R. So there, if we check just for the one photon detection probability at one of the two detectors, then it will not show any interference, because there is no sinusoidal terms there, like cosine or sine. Whatever it will get is a constant thing, which is 4R. That means a illumination will be there only. So this is the second part, that to find the one photon count rate at detectors ds and di, and you know how to calculate that now. Just consider this will be RSS dash, and this is for the ds, just small printing mistake. Now it is telling about the part C, which is referring to the figure below, this figure. Then it is telling that assume that x equal to 0, calculate the coincidence count rate RSI as a function of the displacement y if the central wavelength of each of the signal and auxiliary field is lambda s0. Find the fringe period of the coincidence interference pattern. The above setup is the idea of quantum lithography. For more details, refer to this paper. You can see this paper, Boto et al. For this knowing the quantum lithography. But let us not go into those details. Rather, let us solve this problem, that how to do this. Similar manner, we will find out the two-photon path diagram for this. Then what we will get, that is what we need to know. So what it is telling here, what we need to find out is that calculate the coincident constant as a function of the displacement y. So either the two of them are transmitting or reflecting, then only it will happen. If this is reflecting, this is like going to this reflecting, and this is directly reflecting from this to this. Sorry, this path will also be drawn here. Just forgot again. So this is for the reflection and this is for the transmittance. This is not forgot actually, this is just for purpose. This is purposefully done here, like to understand that if this photon is going through this path, and if it comes from these two direction, like from this path only, then what phase it will add, and if it comes from this path and go to these two detectors, then what will be adding in the for this case. So again, just need to find out phi s1, phi i1, phi s2, phi i2, then delta phi, that is 0 here, delta L dash is also 0 here. You just calculate it by yourself, and delta L equal to y. Because by now you have learned about two-photon interference a lot, you have heard about Hongomandel interference a lot. So what you need to do is just to calculate them again and again for any of the cases, whatever it is given, and you can calculate the delta phi also. So once you have this, once you know this delta L, that is a path length difference, delta L dash path length asymmetry, and delta phi phase difference, then you can substitute them in the equation 5, which I have mentioned as 5, this equation. This is the main equation that you need to know and need to remember. Then if you after substituting all of them in the equation 5, we will get this equation 2r into 1 plus gamma y cos k0 y, where we are considering r1 equal to r2 equal to r again. And again, this k0 can be written as 2 pi by lambda is 0, as it is mentioned in the question, that consider if the central wavelength of each of the signal and idealized lambda is 0, and find the fringe period of the coincidence interference pattern. So where lambda is equal to 0 is the wavelength of each of the signal and ideal photons. Thus we see the fringe period is 2 pi by 2k is 0 equal to lambda is 0 by 2. Okay. Because you know how to calculate the fringe period from the fringe pattern. Note, and there is a note that if we used a classical light at lambda is 0 instead of two-photon noon state at lambda is 0, the fringe period will be lambda is 0 only. In fact, if we use n photon noon state, the fringe period would be lambda is 0 by n. Okay. Alright, so this is the first question and the last question of the previous discussion session. So these are the questions that I wanted to mention and solve, and so you wanted to show the schematic diagram and wanted to show you that how to solve these kind of problems. So please go and practice them very more than 2 times to get all of the information and get to be used to it. So get used to it. So once you so that will be helpful for your examination purpose, I can guarantee that. So this is the first problem, and this is literally these are the you have already reached to the concept of quantum lithography. If you want to know more, you can visit the Boto et al. Paper, where you can type that in a Google and learn a lot of things about that. So today you learned a new concept about quantum lithography from the problem itself. So these kind of problems are the very standard and very high-end problem in this field. So don't feel if you are not able to solve it, then it's fine. You will be able to solve it eventually with the time. And these are literally solving a heavyweight problem. So don't worry. So but with this thing you will be you are able to understand that what is quantum lithography. You know that like when you use, like if you have some semiconductor industry and you want to make the things very smaller and decode more number of chips or more number of smaller integrated circuits into a semiconductor platform, then you need to do it much more finely to be able to encode more and more chips and whatever the things are. For that reason, if you can do that within whatever you can, it is very necessary nowadays to make everything more smaller, more available, and things are very chic and very uh, very handy nowadays. And to make it handy, the lithography is one of the main thing that we use in the industry. And quantum lithography, if now it is possible with the two photon, like quantum with the entangled state, it is possible to create two photon known state, which is giving us 2 times better than the previous thing. But if you use in photon known state, then it will be even more better for for the quantum lithography. Like it will be able to do much more smaller stuff on the semiconductor platform. So this is the thing, through the problem you have learned about what is quantum lithography also. So now after discussing this thing, I will go to the theory part, which is like first the Bell inequality. I will discuss about the EPR paradox and Bell inequality, whatever we were discussing in the previous class. And before that, we will take a short time gap, or like rest for few minutes before we start with the theory part of this Bell violation and the discussion. Okay, and please bear with me for the noisy environment from the dogs and etc., because I am in wherever I am, I cannot control those things. Okay, so please bear with me, and let us wait for a few minutes. Okay, so let's start our discussion on the we'll continue on the topic that can the quantum mechanical description of physical reality be considered complete. We answered the question in the previous class, and we started talking about the EPR thing, the Einstein Podolsky thing, and how the quantum mechanics the uncertainty principle is violated with the two photon state. And then we were discussing about EPR paradox, and then we talked about that there is need of some hidden variable theory. So today we'll talk about the hidden variable theory, then Bell's inequality, whichever is told there in the lecture. But before that, I will start with this maybe I will go there. Yes, I will start with this mathematics, because in the previous session I was just telling you about the stuff, but I have not shown that the mathematics. So what I was telling is that if you know about the position of one particle, then simultaneously cannot know the position of the other position momentum of that particle simultaneously. When we talked about the two photon state and entanglement generation, so we analyze and we reach to this conclusion that this is not true anymore. There is some possible thing that some problem is happening here. So these become the apparent contradiction to this first principle of quantum mechanics. So now let us consider a system consisting of two particles. The particles have a common past and may have had interactions in the past, but they are now space-like separated, and this is what is the two-photon state. And for that, let us assume that the wave function corresponding to the two particles can be written as this psi x1 x2, which is equal to integration minus infinity to infinity psi p x2 up x1 dp, whatever it is showing over here in the first line. Okay. Now, this wave function is a continuous coherent superposition of two particle wave functions, which are psi p x2 and up x1. This means that if we happen to find the first particle with wave function up x1, then the second particle is guaranteed to be found with the function psi p x2. Now let us take a very specific situation where psi p x2 is equal to e to the power minus ip x2 minus x0 by h bar, and up x1 equal to ip e to the power ip x1 by h bar. So we can write the psi x1 x2 in this manner, which is showing in the next line, second line of this. So we see that up x1 equal to the power ip x1 by h bar is the eigenfunction of the momentum operator, which is p cap is equal to, where momentum operator is the p cap equal to minus ih by delta x1, that we know, of the first particle with the momentum eigenvalue p. Similarly, psi p x2 equal to e to the power minus ip x2 minus x0 by h bar is the eigenfunction of the momentum operator p2 equal to minus I h bar delta x2 of the second particle with eigenvalue minus p. So if we measure the first particle and find it be in the momentum eigenstate up x1 with momentum p, then the second particle is guaranteed to be in the momentum eigenstate psi p x2 with momentum minus p. Next, let us write the above two particle wave function as whatever I have mentioned, and further we are writing this as in terms of delta function. In the next third line we can write this this like this, right, and the second part like this, and dp is separated. Now it is integrated over dx and dx dash, because x and x dash are dummy variables, so these are two different integrals, that's why we are using x and x dash. So further continuing on the next level, we have this e to the power minus ip x dash by h bar dp, and this the two Dirac delta function, one is x minus x2 plus x0, one is x1 minus x dash. So from this again we can write the Dirac delta function, which is delta x minus x dash. This is just nothing just but the writing in terms of Dirac delta function, you know very well. Which you know very well. So now for delta we are integrating using another integration again. Then what we are end up with the delta x minus x2 plus x0 and delta x1 minus x dx. and then we can write this first Dirac delta as phi x x2 and next as Vx x1 dx, where phi x2 and Vx x1 are these. Okay, so what does this mean? We see that Vx x1 equal to delta x1 minus x is the eigenstate of position operator x1 cap of the first particle with eigenvalue x. Similarly, phi x x2 equal to delta x minus x2 plus x0 is the eigenstate of position operator x2 cap of the second particle with eigenvalue x plus x0. Thus, if we measure the first particle and find it to be in the position eigenstate Vx x1 at x, then the second particle is guaranteed to be in the position eigenstate phi x x2 at x plus x0. Comparing the above two set of observations for the two particle system, we find that the second particle can either be in the momentum eigenstate or be in the position eigenstate depending on the measurement performed on the first particle. Okay. But according to the first principle of the quantum mechanics, a particle cannot simultaneously be in the eigenstates of both position and momentum, which is stated in the Heisenberg-Onsarden principle. But this is apparent contradiction with the first principle of quantum mechanics, and it is referred to as the EPR paradox, and this led to EPR to conclude that the quantum description of physical reality is not complete and that it should be supplemented by postulating the existence of hidden variables, the specifications of which will predetermine the result of measuring any observable of the system. EPR's inherent belief was that the predictions of quantum mechanics are correct, but only as a consequence of statistical distribution of some hidden variables. Now, this hidden variable interpretation of quantum mechanics was formally introduced or constructed by David Bohm in 1950s. Bohm believed that hidden variable theories lead to precisely the same results for all physical processes as does the quantum theory, while providing a precise and continuous description of all physical processes. And for quite some time, there was no conclusive way to test the validity of these two theories. Then in 1964, John S. Bell came up with his inequalities, an experimental violation of which ruled out the local hidden variable interpretation of quantum mechanics. But now let us discuss about this hidden variable theory, how this was nullified or eliminated, and what does it mean. Let us have some interpretation of it. So with the conclusion of EPR, which is the quantum mechanical which tells that the quantum mechanical description is incomplete, now this conclusion EPR also hinted that there is that can instead work out a theory in which it will be possible to get rid of this apparent non-locality of quantum mechanics, and this suggestion was later pushed forward by de Broglie and David Bohm, whichever I was telling just right now, and they worked out that it is what is known as the hidden variable theory as an alternative theory to quantum theory. A hidden variable theory can be understood as a sort of as a set of a kind of like a set of rules that are imposed on the two particles, such that the statistical predictions of quantum mechanics is reproduced without having to use the notion of entangled state. Basically, the idea was to nullify the apparent and nullify the idea of or eliminate the idea of apparent non-locality of quantum mechanics. Okay. So, for the statistical prediction of quantum mechanics, it reproduced with the without having to use the notion of entangled state. Now, this figure which is showing in this slide is a cartoon illustration of the quantum mechanical versus hidden variable model description of entanglement. The left hand side is showing the quantum entangled model which is going on, which is at that moment in 1960s the whatever the quantum mechanics is developed, based on that this is the quantum entanglement, and based on the hidden variable theory which is based on the hidden variable theory which de Broglie, David Bohm, they have worked out based on the EPR paradox. This is shown with the hidden variable model in the right hand side pictures, whereas the left hand side picture is saying that source of entangled photons are generated through this, and in the hidden variable model the sources with some hidden variable correlations but not entanglement, because we want to nullify or eliminate the idea of non-locality of quantum mechanics. Okay, so people thought that there is something hidden variables which we don't know, which is that's why the quantum mechanics is incomplete. And now, based on these, they have developed the hidden variable model. Now let us have a look that what quantum mechanical wave function tells and what hidden variable hidden variable theory model tells, in terms of taking some examples. Okay, and that's what it is showing in the first set of examples, which is shown over this ABC. So it is measurement outcome is telling that if the first particle is horizontal, then the second particle is also horizontal. This is what, for that, quantum mechanical wave function will be psi equal to kth, and that can be generated with the entangled photon state. Now hidden variable theory model came and it tried to interpret this, and they tell that maybe it is possible if both the sources emit simultaneously and both sources emit photons with horizontal polarization. Okay, so we can eliminate the with this measurement we can eliminate the idea of quantum entanglement. Now next example, the B. It is saying if the first particle is 45 degree polarized, then the second particle is also 45 degree polarized, and in the quantum mechanical wave function form we can write psi as ket 45. With the hidden variable theory model, it can also be interpreted. They are saying both sources emitted simultaneously and both sources emit photons with 45 degree polarization. No issue. Now third example, measurement outcome of the is like something like this, that if the first particle is horizontal, then the second particle is also horizontal, and if the first particle is vertical, then the second particle is also vertical. And based on this, the quantum mechanical wave function can be written as psi equal to 1 by root 2 hh plus vb and 1 by root 2 plus 45 plus minus 45 minus 45. Either it can be both horizontal and or it can be both 45 and minus 45. Okay, and then can we generate this kind of wave function using the hidden variable theory and not by using the two-photon state? So the answer is again yes, both sources emit simultaneously, and 50% of the time both sources emit horizontal polarized photons, and 50% of time both sources emit vertically polarized photons. All right, up to these also it is fine. Now the next example came, for which the measurement outcome is expected as like if the first particle is horizontal, then the second particle is also horizontal. If the first particle is vertical, then the second particle is also vertical. If the first particle is 45 degree polarized, then the second particle is also 45 degree polarized, and if the minus 45, then it is minus 45 degree polarized. Like that means the same thing, but now think about the hidden variable theory model. Can there be such kind of source which can generate this? Maybe you can take this as a homework problem also. If you can find this, then people will be happy that hidden variable theory may be true. But actually there are no such kind of sources which are available, which I have just mentioned what need to be done. Then practically it is not possible. The main question is, can one construct a hidden variable model for every measurement outcome that can be explained using quantum mechanics? We see that for a lot of situations one is able to make a hidden variable model. But one needs to be sure if this can be done for any general measurement outcome. And for quite some time, there was no way of either proving or disproving this. Unless otherwise, in 1964, John Bell proposed a decisive test to check whether that whether or not the local hidden variable interpretation of quantum mechanics were compatible with the statistical prediction of quantum mechanics. Bell formalized EPR's idea of deterministic world in terms of the local hidden variable models. He showed that for a single particle system, local hidden variable models produce all the results correctly. However, in the case of the system consisting of two particles, the hidden variable models do not correctly predict all the results which are predicted correctly by quantum mechanics. He then constructed an inequality and proved that the quantum mechanical correlation could violate the inequality. But the correlation based on the hidden variable model must satisfy it. Bell further showed that for the suggested hidden variable model to violate Bell inequality, they have to be non-local and would have to involve faster than light propagation as well. In his own words, in a hidden variable theory, like whatever Bell is saying, Bell has this is from his paper. I am just quoting that in a hidden variable theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Moreover, the signal involved must propagate instantaneously so that such a theory could not be Lorentz invariant. A popular description of the concept of non-locality and Bell's inequality is present in many papers, like you can follow Kiewit or Hardy. Okay. So based on this, then in your lectures, it was discussed about the Bell inequality also. How we get the Bell inequality? The detailed calculation is shown in your lecture notes. So I should not go and tell those show those mathematics again. There is no reason for that, because you have already you are already aware and you already know about them. But from the Bell's theory, from the Bell's inequality, you got this inequality in your lectures, right? Where we have a parameter called S, which is called Bell parameter, written like this, and for hidden variable theories, S is less than equal to 2, and for otherwise for quantum correlation, S less than equal to 2 root 2. So if we can see that S less than equal to 2 root 2, then it is called Bell violation, or proving Bell violation theory, or it is Bell violating the Bell's theory, like Bell violation. This scenario is overall called the Bell violation. And there are many experiments which are discussed by Professor Anand K. Jha in your lectures, that where you see that there are many experiments which are showing that Bell violation is true, and we are getting 2 root 2 for quantum correlation, less than equal to 2 root 2 for quantum correlation. So from these we can understand that quantum mechanical wave function does violate Bell inequality. Therefore, a hidden variable description of quantum mechanics is not always possible. The first convincing test of the violation of Bell inequalities was performed by Alan Aspect et al., recipient of Nobel Prize 2022, and using and you know that the Nobel Prize was received by three of them. One is Alan Aspect, one is Gillinger, another one I am forgetting at this moment, but yes, the three of the Nobel laureate got Nobel in 2022 for their remarkable work in this direction of quantum entanglement. And an aspect at all has used the correlated photons produced in atomic cascade. Since then, using entangled pair of photons produced by parametric turn conversion, violations of the CH-SH forms of Bell's inequality have been observed for various degrees of freedom, including polarization, phase and momentum, time, energy, spatial parity, frequency, and orbital angular momentum. Even Anand has paper, you can see there. Even Professor Anand Jha has paper there. You can see there that you can visit all of the papers. If any one of you wants to get the papers details, please feel free to ask me. I will be very happy to share with you. So the results of these experiments, all of these have strongly confirmed the predictions of quantum mechanics and have provided very strong evidence against the local hidden variable interpretation of quantum mechanics. Alright, but all of these, whatever we are talking about, these testings are entanglement verification or certification, not quantification, of course. We can tell if entanglement is there or not. How much, that we cannot say. We have not discussed all of these details about, and there is actually a loophole, and current scenario is also looking for is also going towards that direction. And if you find literatures in this direction, you will be able to know that there are still many things left here to do. So there are two broad tests for verifying entanglement. One is through Bell inequality violation, and the other one is by doing EPR correlation measurement. The original Bell inequality test was meant for verifying entanglement of two particles in situations in which each particle lives in two-dimensional Hilbert space. However, more recently, Bell inequalities have been seen, have even been derived for higher dimensions. A Bell violation test involves two-photon interference measurement. The measurement need to be performed in more than one basis and mostly two conjugate basis in order to calculate the Bell parameter S. If the Bell parameter greater than 2, the state of the is said to be entangled. I am very sorry, again there is some mistake in the here. It should be greater than S should be greater than 2. Again, please consider my mistake. It will be greater than 2. And the other method for verifying entanglement, and it will also be greater than 2 root 2. So this is a lower bound like 2 or lower bound 2 root 2 for hidden variable series and for quantum correlation. Please, I am extremely sorry for this. Please correct it. Okay. Now, if the Bell parameter is S greater than 2, the state of the two particle is said to be entangled. The other S less than equal to 2 for hidden variable series. Now if you found S greater than 2, then the two particles are said to be entangled. I am correcting my words. I have made some mistakes, so please hear or listen very carefully. If S less than equal to 2, then for hidden variable, that means less than equal means either equal to or less than, then it is true for hidden variable theories. But if the Bell parameter S is greater than 2, then it states that the two particle is said to be entangled. The other method for verifying entanglement is by doing an EPR correlation measurement, which I have shown in this slide with this written as NPTEL in this part. This is showing NPTEL because this is taken from the lecture notes itself, where you can get this thing. So as I was telling, that the other method for verifying entanglement is by doing EPR correlation measurement. And the test is specifically suitable for entanglement of continuous variables as opposed to the Bell inequality. For Bell inequality, we need to have discrete two-dimensional variables. That's why for Bell violation is easy and is viable to do in the polarization basis, but not in the higher dimensional basis. But EPR correlation measurement we can do in the in a higher dimensional and in continuous basis also. So what I was telling, that this EPR test is specifically suitable for entanglement of continuous variables as opposed to the Bell inequality test, which is suited for only for the finite dimensional system, like the Bell inequality. So Bell inequality is for the finite dimensional system. For the EPR correlation, it can be done in the continuous variables basis in the infinite dimensional basis in dimensional system. So for EPR correlation measurement, one does not need to perform a two-photon interference experiment. What is required in this case are uncertainty measurement in two non-commutating bases. We will now so that's what it is showing here in this slide, that delta x conditional 1, delta p conditional 1 less than equal to h bar by 2, then it is entangled in position and momentum. This is just opposite to the uncertainty principle. What we know from the uncertainty principle, that delta x delta p greater than equal to h bar by 2, then it is uncertain, following uncertainty principle. But if you can show that delta x delta p less than h bar by 2, then it is entangled in position and momentum. Similarly, if delta t delta e less than h bar by 2, then entanglement in time and energy, and delta phi delta l less than h bar by 2, then it is entanglement in angle and orbital angular momentum. Okay, so entanglement means simultaneous. Again, another thing is left. I'm sorry. Psi is HV and 45 minus 45, and if not equal to psi and u, the psi ket u, like in case it is inseparable, then we can show the polarization entanglement also. So entanglement means simultaneous correlations in two conjugate variables and the inseparability of the two particle state into individual particle states. This is what is EPR measurement. And these are the verification techniques, two verification techniques. One is Bell violation, another is EPR measurement, to check if the entanglement is present or there or not. There is again another something called entanglement and formation, inseparability, and you can check it with the entanglement of formation also, because that depends on the experiment situation. You can decide, you have to decide that what you actually calculate, either Bell or Bell violation you can do, or the EPR measurement, or the you can calculate entanglement of formation. All of them are entanglement verifier, not the not the quantifier, but the verifier or certifier. So this was the whole thing, that you guys now know about quantum entanglement, what is entanglement, what is hidden variable theory, what is EPR paradox, what is Bell violation, what is Bell inequality, what is entanglement verification, how to do entanglement verification with the Bell violation or EPR measurement. In the week 11 also you will get to know about the entanglement of formation. So all of the things you are aware by now, what we wanted to convey to you. So and after that we will of course get to know about one of the certifier, which is called concurrence, and that we can do only for the two-dimensional basis in the polarization. Not only polarization, whatever is there, if we do the two-dimensional basis, then we can use the concurrence also. And that concurrence, the concept of concurrence will be introduced in the next week. For now, these are the main things that you have learned, and these are huge topics and so interesting, and of course, as many of us are very curious about to know about quantum entanglement, what is EPR paradox, and all of those things, those are discussed in this discussion session as well as in week 10 lectures also. So by now you have the idea of the quantum entanglement, what is EPR paradox, what is hidden variable theory, what is entanglement verification, how can we do with the Bell violation or EPR measurement, what are they. Even there are several experimental schemes are shown to you and stated to you in the lectures. All right, so these are the things that I wanted to mention, and recap for further things, like recap to you just whatever is done in the lectures. So that's what I used to give you a synopsis, or an idea or overview about like what is actually going on, what is the lecture, what were the lectures about. So this is the thing. I hope everybody of you are very interested and ultimately understood what is quantum entanglement and how we can experimentally actually verify it. So all right, so now we'll start with some problem. Again we'll come to this problem 2 and problem 3, and again I wanted to show the problem 2 with this schematic diagram. That's why the solution here is provided for the part A. For part B and C I will solve with you, but let me. Okay, but for the timing, you please check this problem, and then we will start solving them. Okay, start solving this question. Please try it by yourself in between that. let us start solving this problem, which is saying that consider the above interferometer. Above means this, below interferometer, whatever it is showing here. A pump field splits into two separate fields with amplitudes V1 and V2 from the beam splitter 1. This V1 and V2. The pump photon down converts in either PDC1, this PDC1 and PDC2. Now this beam splitter 2 is a beam splitter placed as shown in the figure, which is this beam splitter 2, with T square plus R square equal to 1, where T and R the transmission and reflection coefficient respectively, alright. As a function of the beam splitter BS3 position X, like it is moving towards up and down direction, one deserves one photon fringes at dA. So now the question it is saying, every information is given to you, that what is the distance, what are the staffs, what is the angle theta, everything. Now assume 1 theta to be very close to 0, okay, alright, and down conversion to be degenerate, okay, and x less than coherence length, and x less than coherence length of the pump P, where LP coherence and L coherence are the coherence lengths of the pump and the signal idler fields respectively, and 4 is D greater than length of coherence length. Calculate the visibility calculate the visibility of one photon fringes at dA as a function of V1, V2 and T. You know now that how to calculate the one photon fringe, that I have shown in the previous problem, where we have calculated about we talked about quantum lithography, and the previous than that where we got that 2R1 plus gamma 1 minus gamma dash 4x kind of things, fringes. There also we got fringes, here also we will get fringes. So for that here also we need to draw the two photon path diagram. So let us see one by one that what we actually need to do, and part B and part C is very easy, that I will solve in my iPad again. So part 8 is saying, since D greater than D is the distance, this distance PDC1 to mirror and the mirror to beam splitter 3, it is greater than length of coherence, there is no second order interference here. So the one photon fringes obtained at dA, one minute. Alright, so there is no second order interference here. So the one photon fringes obtained at dA can only be explained in terms of two photon interference profiles. So now a photon detected at dA can have its entangled partner go to either dB or DC. dB or DC is, this is a dB or DC. Suppose there are two detectors which are imaginary detectors. Therefore we have RA equal to, if we want to calculate the coincidence of a particular one detector, then we need to calculate RAB, what is the interference between AB, and RAC, although they are imaginary, but we need to consider for both. Now where RA is the one photon count rate at detector dA, while RAB is the coincidence count rate of the detectors TA and DB, and RAC is the coincidence count rate of the detectors DA and DC. We find that there is only one alternative by which the two photons can yield coincidence between dA and DC. So there is no interference involved here, and the coincidence count rate is simply given by RAC equal to K R V1 square, where K is a constant and R is the reflection coefficient of beam splitter 2. Okay, so RAC we can directly write R V1 square, where R is the reflectivity that is mentioned in the question. That there is R is the reflection coefficient, and T square plus R square equal to 1. So we can write RAC equal to K into R V1 square, where K is a constant and R is the reflection coefficient of beam splitter 2. Now next we calculate the coincidence RAB, and for that we need to draw the two-photon path diagram, whatever it is showing here with the 1 and 2. In this case, there are two alternative ways in which the two photons can yield coincidence between DA and DB. Therefore, we need to calculate RAB resulting from interference of the two alternatives. The two alternatives can be presented with the two-photon path diagrams, and which can be written in terms of path length difference and path length asymmetry. Now, phi p1 is equal to pi and phi p2 equal to 3 pi by 2 and phi s1 is equal to 3 pi by 2, and there is the delta L dash will be 2x, right? So from this we can get that delta L equal to x, delta L dash equal to x, and delta phi equal to pi. So let me now further calculate in my iPad. From this we can write delta L equal to x, delta L dash equal to x, delta phi equal to y. Since the pump field amplitude is not the same in the two alternatives, so RAB to R1 plus R2 plus 2 R1 R2 cos K0 delta L plus delta phi, where K0 is the magnitude of the wave vector of the pump field. Okay. Now we can substitute, where R1 is equal to some K amount of T V1 square, R2 equal to K amount which is maybe same V2 square. I will substitute them. Why minus? Because delta phi is equal to pi, so cos, maybe I can write one more step. So here it will go as minus. So for this, so K T V1 square plus K V2 square minus 2K T V1 square V2 square cos K0x. So for the so this is the RAB. Now one photon count rate at TA you can write. That is RA equal to RAB plus RAC, which is equal to, whereas RAC equal to, I have already shown, is equal to K R V1 square. Okay. So now I will substitute. One minute. Okay, so this is the RA, one photon count rate at DA. Thus the fringe visibility you know how to calculate visibility. I have shown multiple times and it is discussed in the lectures notes, and from the beginning we are doing calculation, we are calculating the visibility. So V is equal to, that is the correlation part, and this is that Imax minus I mean by Imax plus I mean. If you do so, then what we will get is this. This is a fringe visibility. Maybe I will get this. Okay. Now the question part B and C. Now we will do this part B and C. Again for you, this is the whole calculation that I have done. Problem 2A, I think so, yes. Now part B is very easy. You please try it by yourself at least once. So I will just read the question. What is the visibility when V1 equal to V2? When V1 equal to V2, visibility is equal to, let me do that, V1 equal to V2 equal to V, suppose, then V square 2 V square T is equal to T. Directly depends on the transmittivity only. In the part C, this is the thing. This is the thing, part B. V1 equal to V2 equal to V. Visibility is equal to 2V square by 2V square by T, that is into T, that is equal to T, which is the transmittivity only. Now the part C is telling that now we replace B splitter 2 with a two-dimensional transmission object with transmission coefficient T rho x rho y. Work out a scheme for imaging this object using the intensity measurement dA. Okay, let me read the question once again. Now replace beam splitter 2 with a two-dimensional transmission object with transmission coefficient T rho x rho y. Work out a scheme for imaging this object using only the intensity measurements at dA. So when V1 equal to V2, then visibility is equal to T. Thus the visibility equals the transmission coefficient. In this case of two-dimensional object, this will take the visibility of rho x rho y equal to the given thing. Therefore, in order to image a two-dimensional transmission object with transmission coefficient given like this, we need to measure the visibility of fringes at dA for every pair of rho x rho y. So what we need to do? We need to measure the visibility of fringes at dA for every pair of rho x rho y. Alright, so this is the answer. What is the answer? It is saying work out a scheme for imaging. So this is the scheme for imaging, whatever it is given. Now we need to measure the visibility of fringes at dA for every pair of rho x rho y. and we will get rho x, rho y in like rho x, rho y, very many pixels, and we will get a total constructive total image. And this is just a scheme of which is called, this is showing the induced coherence scheme, and this is showing the actually the very celebrated experiment doing of imaging undetected photon, which was done by Zeilinger, and he also got the Nobel Prize to 2022. So with these problems, you can actually you can actually get the essence of like what is going on right now in this direction of research. So I hope you enjoy these problems, and you are enjoying this solving these questions as well. So this is very interesting, very important, and give a thought on the details of this problem and try to do it by yourself again. So now we will go to the next problem. Problem 2 is done. This is problem 3, and I'll recommend that please go through this problem once, and try to think and develop some idea and try to solve it by yourself. Then after 5 minutes I'll start it. So let us now start reading the third and last problem of today's discussion session. The problem is saying that consider the situation shown in the figure below for generating a two-photon state. This is assume that the collinear down conversion happens. You know that what is collinear, non-collinear. Collinear down conversion happens in either the forward or the backward pass of the pump through the PDC crystal. This is a PDC crystal. This is going towards this, going towards this. This is a prism. Pump is pump is there. Pump, it is going through the prism. It is going towards this PDC. It can go in this direction. It can again go through this direction, and vice versa. Always, it does not generate the entangled photon. It can go through this direction and again come back and again produce the down converted photon. So in every manner, there can be two signal and two idle. And there is phi phase introduced here, and this is the F point, and the angle between this line, this dotted line, and this signal idler path is theta. Write down the state of the two photons in terms of the mode level C and D. So the two photon state can be written very easily. Thus two photon state is psi equal to 2c 0d plus 0c 2d. So you can see here that write down the state of the two photons in terms of mode level C and D. I can easily write like this: either two photons are coming from C and 0 are coming from D, or two photons are coming from D and 0 are coming from C. So this can be easily written in like this: 2C 0D plus 0C 2D in this manner. Similarly, the field operator the part B is asking that in the limit in which theta is very close to 0, write down the field operator F at the location of the detector in terms of the field operator C and D. The field operator need to be F is need to be written in terms of C and D. Again, very easy. F can be written, let me write the field operator is F cap C cap plus D cap e to the power I phi. As it is mentioned that write in terms of C cap and D cap, that's why C and D. This is C cap, this is D cap, and this is e to the power I phi. A phase is introduced in the D path 3. That's all. And last but not the least, in the limit in which theta is very close to 0, calculate the two photon absorption probability at the detector location in terms of phi. So the two photon absorption probability that we need to calculate in case of theta very close to 0. Psi F dagger F psi. Using the form of the operator F and the state psi above, we can obtain this. This is the two photon absorption probability. So what we need to do now? We need to substitute F and F dagger for all of these F dagger, F we know. Then finally if you calculate, then you will get 4 into 1 plus cos 2 pi. This is actually given in your assignment problem also. So if you follow these discussion sessions, then it will be very helpful for you. You will be able to solve the problems from your assignments. So this is the last questions that I wanted to discuss. So let us have a look again in the question, and then we will wrap up the session. Maybe you can check it once here. Okay, fine. So let me formally end today's discussion session. So these are the topics and things that I wanted to discuss today. So today is week 10 of this Coherence and Quantum Entanglement course, and I am your TN Ilaksha Shanapati. So today we have discussed a lot of interesting things, like we have first of course I have discussed the homework problem and what a new problem, and let you know that how to solve these kind of problems just by using two-photon path diagram. And then we reached to this part of our discussion where we discussed about Bell's inequality and EPR paradox, and what is the hidden variable model. After talking about the hidden variable model, how it was eliminated, and how the Bell's inequality come into the play, and what is Bell inequality, how that we learned, and you have also seen in your lectures. And now after all of these, we get to know about the entanglement verification, that you can verify it in the using Bell violation or EPR measurement. For the finite basis, you need to do with the Bell violation. For infinite dimensional continuous basis, you can use EPR measurement. And what are those we learned also. And in between that, of course, with the first problem we came to know about the quantum lithography also with this problem. And likewise, after this doing this problem while doing this problem too, we came to know about the quantum imaging with the undetected photon, which is just a concept of induced coherence method, which is shown in this problem. So this was a very interesting problem which we have solved. We have also discussed about the novels of 2022, which were dedicatedly given for this the research in this direction only to the eminent three professors or physicists in this field. And then we solved this problem, and at last we solved this problem 3, where it was a very sweet kind of problem, which we can solve very quickly. And this is just another kind of reference for you also, that how you can get the two-photon absorption probability with a single detector, with at the detector with a single detector also, by using prism also. So this is the summary of today's class. And of course, as I mention every time, that you will get all of this discussion session recording video and slides in the YouTube. Once again, this is a YouTube channel, and it is shared with you in this chat section also. You can find it. there is a Google Drive link where you will get all of these things will be uploaded. You will get that, and this is my mail ID. You can mail me if you want to discuss anything, and you can use the Ask a Question portal also. You can use or the comment section of the YouTube video also. So that's all for today. I hope you guys have learned a lot of things and enjoyed these sessions, and of course enjoying these sessions. So only two are left. One is 11 and week 11, and another is week 12, and there will be a summary discussion on 14th of April. 14th of I think so, yes, 14th of April, I think from 11 to 12 or 10 to 11, something like that, where we will wrap up the course. So this is all for today's week 10. See you again in the next class. Bye for now.